Okay, don't let me go past this line without moving it. That'll help us remember. And let's continue. Where's my chart? There we go. Okay, so recap with what we were talking about last week. We were talking about functions. In particular, for the purposes of this class, anytime we were talking about functions, we were talking about functions from a set to a set. So if I give you f as a function from the set x to the set y, then we know that f maps everything in x to something in y, right?
Yes.
So we know that for every little x in big X, there exists little y in big Y, such that f maps that x to that y. Everything in x, for everything in x, there exists something in y, such that f of x equals that thing in y. So if we know that f is a function from x to y, we know that this is true. Furthermore, we know that given two things in x, two things in the domain, if they're equal, then what they map to has to be the same thing. In other words, I can't have f of 1 maps to 2 and f of 1 maps to 3.
Right.
If f is a function, for every input, it has one and only one output. That's what we're saying here. So for any two inputs you pick, for any two things in the x, any two things in the domain, them being equal implies their outputs are equal. You follow that?
Mm-hmm.
Anything confusing there? So that's what we had for functions, and then we talked about three interesting properties a function might have. The function might be one-to-one or injective, it might be onto or surjective, and then it might be both of those, which we call bijective. You remember any of that?
No.
Alright, so let's go over it. So first off, we said it was possible for a function to also be one-to-one. What did we mean by or injective? What did we mean by one-to-one or injective? We mean for any two inputs, if their outputs are the same, that implies the inputs were the same.
Right. Okay.
That's what it meant to be one-to-one. So remember, a function, if the inputs are the same, the outputs are the same. If the function's one-to-one, then the outputs being the same implies the inputs are the same. Does that make sense? So that was one-to-one or injective, and then onto or surjective just means that f of the domain is the entire codomain. It uses up all of y, not just some of y. So when it's a function, all we know is that it maps everything in x to something in y. We have no clue if we used up all of y. Does that make sense?
We didn't necessarily.
I can make a function f from the real numbers to the real numbers, where I map every real number to the number 1. Right? So I can make a function f of x from the real numbers to the real numbers, where f of x is always equal to 1. So f from r to r by this. This is a perfectly valid function. It maps everything in here to something in here. We mapped everything in here to 1. Right? This is not on 2, obviously, because we only mapped to 1. 1's the only thing in here we mapped to. We didn't map to everything in here. If I did the function f from r to 1, okay, now we've got an onto function. We used up all of this set. That's a curly brace. Does that make sense? Right. So that's what we meant by onto or surjective. We map to everything in this right-hand set or the codomain.
Does every function use every x?
Every function has to use every left-hand element. It has to map everything in here to something in here. For all x, there has to be some y such that f of x equals y.
What about that?
Huh?
Continue.
You got it?
Yeah.
Okay. So any questions about one-to-one or on-to? And bijective was the easiest one. That just meant it's 1-to-1 and on-to. Or it's surjective and injective. Injective and surjective. It's bijective. Has both of them. Has both the properties. Bi, too. So we good with the recap?
Yep.
Okay. So now we're going to do some basic proofs, proving that certain types of functions have certain of these properties. Going to be real easy proofs to help get you comfortable with the properties. So we're going to look at f, the function from r to r by f of x equals x squared. Is this function going to be 1-to-1?
No. Or yes, one. No.
No, it's not going to be 1-to-1. Is it going to be on 2?
No.
No, it better not have either property. Now let's prove it. So we're saying that this function isn't 1-to-1 or on 2. It's neither of them. And we're going to prove it real quick. We're going to prove it with counterexample. Observe that, what's f of 2?
4.
4. What's f of negative 2?
4.
4. So f of 2 equals f of negative 2, but that 2 is not equal to negative 2, showing that it isn't 1-to-1. Remember, if it's 1-to-1, then anytime f of a equals f of b, you better have a equals b. Here we have f of a equals f of b, but we do not have a equals b. It's a counterexample. We found a case where we satisfied the antecedent, but the conclusion was false.
Okay.
Make sense? So, that's how we showed that it isn't 1-to-1. Okay, how are we going to show that it's not on 2? Observe that for any x in the real numbers you pick, then x times x is greater than or equal to 0, right?
Right.
X squared is greater than or equal to 0. And negative 2, which gives us that negative 2, is not in the image of this function.
Right. Meaning we've mapped it already to something.
The function always outputs things greater than or equal to 0. Therefore, negative 2 is not in the image of this function.
I think where he's confused is why negative 2.
Yeah. I'm doing a counterexample. I'm just finding a number.
Right.
Same reason up here. Why did I use f of 2 and f of negative 2 instead of f of 3 and f of negative 3? I'm just coming up with an example. So I just needed to find some number, I chose negative 2, such that no matter what you choose to square, you'll never get negative 2.
Mm-hmm.
There's no real number that you can square such that you get negative 2. So negative 2 isn't in the image of this function.
Turns out it's all that.
Because the image of the function is always greater than or equal to 0.
Okay.
Yeah, maybe help clear this up. Negative 2 is not in there, which is equal to all the numbers from 0 to infinity. Right? That's the image of that function. Anything weird there? Nice, simple?
Yeah.
Okay, let's do another one. F of x equals 3x plus 1. Is this going to be 1-to-1?
Yes.
Yes. Is it going to be on 2?
Yes.
Yes. This is just a line of some sort.
I'm just literally looking at the graph like 3x.
Right, this is just going to be a line of some sort. Oops. I don't know what exactly it's going to look like, but it's going to be something along the lines of that. It's just going to be some line in the plane. It's going to map every x to one and only one y.
Okay.
There isn't any x I can pick where I don't get a y. Furthermore, there's no duplicate y's. Before, we had a parabola as our function with the one up here. What did that look like? That looked like, that looked like, come down a little bit. That looks something like this.
No.
Notice that there's lots of x's, or there's lots of duplicate y's. I'm going to get a 2 over here and a 2 over here. Right?
Mm-hmm.
So there's lots of duplicate y's. So it wasn't on 2. So it wasn't 1-to-1. And then it's not on 2 because my function never gives me values down here. It never gives me negative values.
Okay.
Right? Here's negative 2.
Mm-hmm.
The value of this function is never negative 2. When I give it negative 3, what do we get? We get 9. When I give it negative 2, what do we get? We get 4. When I give it negative 1, what do we get? We get 1. My picture is terrible, but you get the point.
Yeah.
So for any x I pick, I can find its value. Right?
Mm-hmm.
But it's never going to be a negative number. So I'll never get negative 2. Another way to say it is the height of this curve is never negative 2. There's a point where it's 0, there's a point where it's 1, there's a point where it's 2. For any number you pick greater than or equal to 0, I can find you a point on this function where it's that height. Right?
Mm-hmm.
But I can't do it for any negative number you pick. So it's not on 2 because there are some values in this right-hand set that never get mapped to, namely negative 2. And it's not 1 to 1 because I can draw a horizontal line through here and hit it at 2 different points. So both those points have the same height. So whatever this x is and this x is, they both map to the same value. With me?
Yes.
So that's thinking about the geometry of the curve, how you can determine really quick if it's 1 to 1 or on 2. It's 1 to 1 if any horizontal line I draw only intersects it once. That means it's 1 to 1. We never get two y's coming from the same point. That's 1 to 1. And then it's on 2 if we get every y. Every y down here all the way up to here. So any vertical line we draw, is obviously going to be 1 to 1 and on 2.
It goes outward and downward.
Yep. For any y you pick, I can find an x that gives me that y. And then it's 1 to 1 because for any horizontal line you draw, you'll only ever intersect this line once. Make sense?
Yeah.
So that's what Jacob was doing to know right out the door, hey, this is 1 to 1 and off 2. But we'll prove it. Okay, so first off, we need to prove that it's 1 to 1. How do I prove it's 1 to 1? I assume I have two a's, I assume the antecedent, and show that implies a conclusion. I'm going to show that if you have two numbers, a and b, such that f of a equals f of b, then you're for sure going to have a equal to b.
Mm-hmm.
So let's prove it. Let a and b be real numbers such that f of a equals f of b. Well, what does it mean if f of a equals f of b? That means f of a, 3a plus 1, equals f of b, 3b plus 1.
Right.
Subtract 1 from both sides, divide both sides by 3.
Okay.
A equals b. So if f of a equals f of b, then a equals b, showing it's 1 to 1.
That was pretty simple.
These were one of my favorites.
It's very simple. It's one of those things that the first time you come across, you're like, how would you prove that? And then when you see a proof, you're like,
Oh.
yeah, that was
Discrete
easy.
math, when I ran into these, it just felt good.
No. If you can't figure it out, then it just sucks.
Yeah.
Well, we're not there yet, so you'll get double advantage when we come across in discrete math. If you can get past proof by induction.
I don't know if I can.
No one ever does.
I still can't tell you.
And he also got the calculus again. We're going to have to cover that at some point here because our proofs are going to have to be proof by induction. We haven't covered that, have we? I guess I'll just cover it whenever it comes up. Alright, anyways, continuing with this proof. So we proved that this function is 1 to 1, now we need to prove it's on 2. How do you prove it's on 2? I need to show that for any y you pick, I can find an x that maps to that y. Therefore, every y is used. Does that make sense?
Yeah.
So I say pick any y you want, and I'm just going to randomly choose this x equal to y minus 1 divided by 3. Now notice, if y is a real number, then y minus 1 divided by 3 is also a real number, right? So x is some real number. So you chose some random thing in here. I said, look, I picked an x in here, and I'm now going to show you that f of x happens to equal y.
Right.
Okay.
The reason
So-
you'll see why you chose that number.
Yeah.
Yeah.
So now he does this all the time.
Right.
So you pick any y you want, and then I pick this x. With me so far?
Mm-hmm.
Then observe that x is a real number, and that f of x, what is f of x? That's 3x plus 1, right? But I have y minus 1 divided by 3 times 3. 3's go out, that just leaves me y minus 1 plus 1, which is equal to y. So f of x equals y. So for any y you choose, here's the x such that f of this x will give you y. You say pick y to be 10. I say, okay, then what's my x? My x is 3. And notice that, go back up to our function. Where's our function?
Right there.
If you pick 10, I choose x to be 3, so 3 times 3 is 9 plus 1 is 10.
Right.
Make sense?
Right.
Yep.
So, for any y you pick, I found an x such that f of x is equal to y, showing that f is on 2.
That's cool.
Follow those proofs? Okay, let's do some more. Let's do g is a function from r to r squared. What's r squared?
The real number squared.
The real numbers.
The real number squared, so it's going to have 1, 4, 9, 16, right?
Oh, no. Isn't it like a plane?
Yes, it's the plane. It's r cross r.
Right.
Is what r squared means, or r to the 2 means. R2 is how I should say it. It's taking all the real numbers and crossing them with all the real numbers. So it's all the ordered pairs you can make using 2 real numbers. Or in other words, it's every point in the plane.
Okay.
So you can think about r as being the real number line. Here's r. Then r cross r is the plane. R cross r. Right? We took this real line and we crossed it with this real line, giving us a plane.
Why haven't we been doing that on the other ones? Because we weren't dealing with planes necessarily. We're just dealing with real numbers. With your 2 other examples.
I'm
Why
just giving
haven't we been doing
examples.
r to r cross r?
We can do from whatever set to whatever set we want. I just did it from
Why
r
is it
to
important? Why is it important in this proof? See, what I'm
These
saying
are
is-
just examples to get you comfortable with these notions. There's no reason that we're using r to r2, except for that
we're dealing with functions.
we just picked a random function from 2 domains. We just picked a couple domains, made a function from them, and now we're going to look at, is it 1 to 1? Is it on 2?
Everything in r cross r is going to be an ordered pair, correct?
R cross R is the set of all ordered pairs you can make where the first number is a real number and the second number
Okay.
is a real number.
There was my.
Any point you pick in the real number plane, hence it being called the real number plane, can be expressed as a pair, an ordered pair of real numbers.
Yes.
So you can think about the real number plane as being R2. You can think about the real number line as just being R. For every real number you pick, I can find a point on this line that represents that real number. For every point you pick, or for every ordered pair of real numbers you pick, I can find a point in the plane that represents that ordered pair of real numbers. That's why we call it the real number line and the real number plane. What about R3?
3-dimensional.
Yeah, isn't that this?
Yep, that's this right here. For any ordered triple of real numbers you choose, I can find a point in 3-dimensional space that correlates to that number. Okay, anyways, so we've got some function and it maps everything on the real number line to some point in the real number plane. Right? She is a function from the real numbers to the real number plane, or r cross r. And what's the function going to do? It's going to take x and it's going to map it to xx. So if you want a picture of what this function does, it takes 0 and maps it to 0, 0. It takes 1 and maps it to 1, 1. It takes 2 and maps it to 2, 2. It takes -1 and maps it to -1, -1. Or in other words, it's going to give us this line.
Okay.
So it takes this line, this real it takes the real numbers and maps them to this line. That's what's here, right?
I don't see.
G of x is the point x comma x. What's g of 1? 1 comma 1. What's g of pi? Pi comma pi. Good?
Mm-hmm.
Nice simple function. So we're going to show that it is 1-to-1, but it's not on 2.
It's on 2.
No, it's not. That's one of the reasons to do examples like this. Because you're only used to thinking about these things when you're looking at from the real numbers to the real numbers. And so you lose track of what exactly the definition gives you because you're relying on your intuition for just the examples you've seen 100 times in your life. That's why we enjoy examples like this. Which is exactly why they most likely came up with this one, because it does give you this line. And so you say, oh, lines are 1-to-1, right? No, only if it's from R to R. Not if it's from R to R squared. And we'll show it. First off, let's show it's 1-to-1. How do we show it's 1-to-1? We need to show that if g of A is equal to g of B, then A is equal to B. So let A and B be any two real numbers such that g of A is equal to g of B. But if g of A is equal to g of B, then g of A is equal to g of B. And we proved in set theory that ordered pairs are equal if and only if their left-hand elements are equal and their right-hand elements are equal. Therefore, A is equal to B. What part did you get confused
The
about?
part that confuses how do we define that ordered pairs are equal? If their left hand are the same and their right hand are the same?
The only way that the order pair, come back over here in some scribble space. The only way that the order pair AB is equal to BC is if these two are equal, if and only if A is equal to B, sorry, we need C and D, not the same number. These two are equal if and only if A is equal to C and B is equal to D.
But they're not. A is not equal to B and A is not equal to B.
I know it's given to me that this is true. If I know this is true, then I know this is true. Right? Which one are we doing? I know that g of A equals g of B.
A and B are two x's.
A and B are two things in here such that g of A equals g of B. So all I know about whatever A and B are is that the real numbers such that the image of those real numbers is the same.
In this case, they have to be the same number.
We are proving
I understand.
that, oh crap, I erased it.
I understand, but I'm saying literally in this case, they are going to be the same number count by intuition.
If we want to prove that an implication is true,
We
we assume the antecedent, and we show that implies a conclusion. So I assume I have A and B such that f of A equals f of B. Maybe there aren't ever two A's and B's such that f of A equals f of B. Maybe it's never the case. That's vacuously true. So we only need to worry about the case where the antecedent is true. So if f of A equals f of B, I need to show that implies A equals B. So assume that I have A and B such that g of A equals g of B. I need to show that if this is true, then A equals B is true. But this being true implies this is true, and this being true implies this is true.
Mm-hmm.
Therefore, if this is true, then this is true.
Okay.
Keep track of what we proved. We did not prove that g of A equals g of B. We proved that g of A equals g of B implies A equals B. This implies this is what we showed is true. We didn't show this is true, and we didn't show this is true. We showed this implies this is true.
In this specific example, they're going to be the same number though. A and B have to.
Right, that's what we just showed.
That's
We
what
showed
1-to-1
they're
is.
1-to-1.
Over here, they didn't have to be the same number.
Oh.
F of A equals F of B, but A did not equal B.
I remember what the whole point of the proof is. The whole point of the proof is if you have the same x and you get a different y. If you have the same x and you get different y's, then it's not 1-to-1.
If you have the same outputs, then they came from the same inputs.
Right.
Yes. the image being the same implies the things in the domain were the same.
Perfect.
Okay.
Total sense.
Now we're going to show that it's not on 2. How can we show it's not on 2? Well, observe that 0, 1 is in R2, right? That's a perfectly valid ordered pair of real numbers. But 0, 1 is not in the image of the scene, right? The image of the scene is this line. 0, 1 is a point right here. This point is not on that line. So it's not on 2. Make sense?
No.
No. In order for G to be on 2,
Okay.
then it has to map everything in here to everything in here. Right?
Yeah.
0, 1 is in here.
But it's not.
The ordered pair 0, 1 is in this set.
Yeah.
Is there anything in this set that maps to 0, 1? What's the x I can plug in here so that I get 0, 1 here?
There isn't.
There isn't one. If I plug in 0, I get 0, 0. If I plug in 1, I get 1, 1. There isn't an x that I can plug in here, so I get 0, 1 here. So 0, 1 is not in the image of the sink.
Okay.
The image of the sink is the line y equals x, if you want to think about it that way. And 0, 1 is not in that line, if you think about that line as a set of points.
That makes sense.
So
Good?
is every bounded line not on 2?
I don't even. Every bounded, so you mean a line that doesn't go up for infinity?
Yeah. So bounded.
Is every bounded line on
Not
2?
on 2.
Neither. Some bounded lines are on 2, some are not on 2. Because it's all a matter of how you choose that other domain,
Oh yeah. Okay.
right?
So from the rails to rails.
From the rails to rails, and a bounded function is not on 2.
Oh yeah. Okay.
Because that's what you mean by bounded.
Yeah.
You mean that, well, it's not what you mean, but it's an implication of what you mean by bounded. If the function is bounded, then it can't give you arbitrarily big numbers. Arbitrarily big numbers are real numbers, therefore it wouldn't be on 2. So yes, that is correct. Okay, let's look at another one. We're going to look at H. This time, what are we doing? We're mapping R2 to R.
Which is weird, but yeah.
Okay, it's weird.
Just
So,
saying.
huh?
Just saying. I'm just like, okay, sure.
Yeah, you probably haven't really seen something like this before. Okay, here's how we're going to map R2 to R. H of any point, we're just going to map it to its left-hand coordinate. So we're going to map the point 5, 9 to,
5.
5.
we're going to map the point negative 27 pi to,
Negative 27.
we're going to map the point 5 pi to, we're going to map the point 5, 97 to,
5.
so we're mapping a lot of points to 5. Right?
Oh.
So obviously it's not 1 to 1.
Okay.
Right?
Okay.
There's your intuition. We're mapping this whole vertical line to this point. We're mapping this whole vertical line to this point. Right? Okay. So before we were mapping points to lines, that's what we were doing up here. Now we're mapping lines to points. No, we weren't. Here we were just mapping points to points on a line. Sorry, I lied. This was just mapping points to points on a line. But here, we're going to be mapping entire lines to one point. Okay, so I think you already have the intuition for it's on 2, but it's not 1 to 1. It's on 2 because we're going to use up all of R.
Okay.
For any real number you pick in here, I can find an order pair in here that gets mapped to that number,
If
right?
you ended up using all of R, would you not get the whole plane? You would end up getting the whole plane, wouldn't you? You'd have a line on every X.
Yeah.
Right.
We're mapping every vertical line we can make to just the point where it intersects the x-axis, is one way to think about
But
it.
we're not like on specific integers or anything.
No.
Right.
And we're not really mapping it to these points, we're mapping it to the real number whose x-coordinate is that point.
Right.
Because points are two-dimensional things, and we're not mapping it to two-dimensional things, we're mapping it to just a real number. But for any real number you pick, I can always find a point that maps that real number. So it's going to be on 2. So, you probably already see how the proof's going to go, but let's just do it. So first off, let's show it's not 1-to-1. Observe that h of 0, 1 is equal to 0 is equal to h of 0, 2, but that 0, 1 is not equal to 0, 2. So one counterexample. I found a and b where h of a equals h of b, but a does not equal b. So the antecedent was true, but the conclusion was false. So it's not 1-to-1. This has to be the case for any two numbers, or sorry, for any two things in the domain. I found two things in the domain such that their image is equal, but they're not equal. Everyone follow the logic there? Okay. Now let's show that it is on 2. If I'm going to show it is on 2, then I need to show that for any y you pick, I can find something in the domain that maps that y. So for any real number you pick, I can find a point in here that maps to there. So let y be anything in this right-hand set. Let y be anything in R, and observe that y comma 0, this point, is in the domain. And the image of this point is just y. So for any y you choose, I found a point, namely 0 comma y, that maps to that y. So it is on 2. Make sense?
Okay.
Okay, let's prove another one's a bijection. Oh no, this is a definition. Definition, I think all of you have come across inverse functions before already. Intuitively, you think about it, the inverse of a function is you swap all the x's and y's, right? But in this class, since our functions are always from a set to a set, then our inverse function also needs to be from a set to a set. Okay. So if f is a function from x to y, and it's a bijective function, then the inverse function, which is going to map all of y to x, is the inverse function where for anything you pick in y, f inverse of y is the x, where x was a unique value in big X, such that f of x equals y. In other words, you had a function before where f of x was equal to y, then the inverse function takes that same y and maps it to that same x. We did it over here. If you say f of x is equal to 3x plus 1, then f inverse of x is equal to x minus 1 over 3. If this is your function, your inverse function is this.
Gotcha.
Plug 3 in here, what do you get? 10. Plug 10 in here, what do you get? 3. So this function maps 3 to 10. This function maps 10 to 3. It swaps it, does it backwards. Or one way to think about it is this function undoes this function. How would you describe this function in words? It adds 1, or sorry, it multiplies by 3, then adds 1, right? This function subtracts 1, then divides by 3. It undoes it. They undo each other. So, I already had it written right here, that exact example. So if we have f is a function from r to r by f of x equals 3x plus 1, then we can say f inverse of r, since we know that this is 1 to 1 and on 2. since this is a bijection, then we know it has an inverse. And what is its inverse? It's f of y equals y minus 1 over 3. And how do we find the inverse function? In this case, maybe I'll walk you through that exercise really quick. It's real easy. So I have f of x equals 3x plus 1. Sometimes we like to write that as y equals 3x plus 1, right?
Yeah.
So if I want to find this inverse function, if you're wondering, how did I find this inverse function from this function, instead of just thinking about it, is there just a way to always do it? The answer is yes. All you do is swap your x's and y's, and you're done. But then you can rewrite it prettier if you want. The inverse function of this is x is equal to 3y plus 1. This is the inverse of this. Now you want in terms of y, so what do? You subtract 1 from both sides and divide by 3. So that's y equals, subtract 1 from both sides, so you have x minus 1, and then divide by 3. So you just swap the x's and y's, and you can solve for y. Make sense?
Mm-hmm.
So that's how I came up with those. So I didn't have to think about it. Okay. So that's it for functions being one-to-one, onto, bijective, and for inverse functions. Feel like you're good with that? Or do you want to see more examples of anything? Ready to move on? Alright, let's move on. So, new definition. So this definition is basically to help us. Let's just go over it first. I have an example to show how it helps us, so we'll just write out. So let f be a function from x to y, and let a be some subset of x. Then the restriction of f to a is a function f, and we write it like this, f vertical line a, to tell us f is a function restricted to a. It's a function that maps everything in a to y. So instead of it mapping all of x into y, it only maps a into y. Remember, a is a subset of x. So now we created a new function that only maps part of x into y, instead of all of x into y. Different function, but we constructed it from the function.
Isn't this just like a shorthand way of writing something we've already been writing earlier? Like, didn't we have, we're already taking subsets and mapping them in functions? Subset of functions, mapping them to the same function.
We proved some properties about mapping subsets of functions. So you're probably thinking stuff like, let me make sure I get it right. So if we had f is a function from x to y, and we have a is a subset of x, and we have b is a subset of x, then we prove things like f of a union b is a subset of f of a union f of b.
Oh yeah.
You might be thinking that,
Perhaps.
but that's not what we're talking about now. We're talking about defining a new function from a given function. And the only thing we're changing is we're making our domain smaller. So we are restricting our domain to certain values. So f is a function from x to y, and a is a subset of x. The restriction of f to a is the function f restricted to a. So it's a function from a to y by f restricted to a of x is still just f of x. We still map all our values the same way, we just made our domain smaller. The notation can look kind of dense and like it seems like I'm doing something complex. I'm not. It's the exact same function, we just made the domain smaller. So if I had a picture of some function, like x squared, there's a function that goes from all of r to r. Maybe I only want to look at starting right here onwards. So I get rid of this half of the function. Okay, there's a restriction of it.
It all of a sudden it's 1-to-1.
And now it's 1-to-1.
Interesting.
So we're just making the domain smaller. That's all we're doing.
Right.
So A is the subset of the domain. F restricted to A still does exactly what F does, but now it only takes as inputs values from A instead of values from all of X. Let's look at an example of where this is useful. So we're going to look at the function f from all the real numbers to, remember what this is, the closed interval -1 to 1. It's all the points between -1 and 1, including -1 and 1. With me?
Mm-hmm.
By f of x just equals sine of x. How many of you have seen a sine function before?
Yeah.
Everyone but Peter? Alright. The sine function, if you graph it, it just looks like this.
It's a circle.
And it goes on and it's not a circle.
Well, I'm saying it's a circle. Well, okay, never mind.
It's mapping the y-coordinates of positions on a circle given an angle, but
Yeah.
we don't need to understand that right now. That's trick. All that matters is, what is it? It's a function that waves up and down like this over and over again. Repeats off to infinity in the right, off to infinity in the left. The highest it ever gets is 1, and the lowest it ever gets is -1.
Okay.
Okay? And it sits here and it repeats values over and over again. So it's not 1 to 1. It's not a bijection.
Mm-hmm.
Notice it's on 2 because it maps all the real numbers to something. Or because it maps to every value between -1 and 1, including 1 and -1.
Right.
So we use all the numbers between 1 and -1, but we use them repeatedly.
Right.
So it's on 2, but it's not 1 to 1.
Right.
We want to make a function that is 1 to 1 from this function
Just restrict
Oh,
your
just
domain.
by restricting our domain.
Right.
Okay.
So we're going to restrict our domain, and we just pick, well, it gets -1 here, and it reaches 1 here, stop. And that's what we choose. We could have chosen it anywhere. We could have said from here to here, it's 1 to 1. We happen to choose this one.
Mm-hmm.
So we said, yeah, f from r to the closed interval -1 to 1 by sine function isn't 1 to 1. But now if we let a be from -pi-halves, you don't know that sine at -pi-halves is -1, and that pi-halves it's 1, but it is. So if you restrict it to this interval, right here, the domain to this interval, -pi-halves to pi-halves, then now f restricted to a from a to the closed interval -1 to 1 is now a bijection. It's 1 to 1 and it's on 2.
Okay.
Okay? So nothing weird, nothing complex, right? You took something that was only on 2 and you restricted the domain to also make it 1 to 1.
Is there one where it's a bijection and then you make it not a bijection?
Typically we like to give it properties, not take away properties,
Well,
to make it nicer.
let's say it didn't have any and then you made it a bijection. Like in this one, it was on 2 already.
Plausible.
Right, so we could have started out by looking at the sine function from r to r, and we could have said, oh, it's not on 2. Oh, but if we just replace r here with this closed interval, okay, now it is on 2.
Okay.
But it's not 1 to 1, so now if we replace that with this, now we got a function that's 1 to 1 and on 2. So now it's a bijection, and then for those of you who have taken trig, now we can define inverse sine. Since we now have a bijection, we can create an inverse function.
Right.
And so you'll probably remember, for those of you that took trig, whenever you took the inverse, taking the inverse of pi-halves and 3 pi-halves gave you the same thing.
Right.
Taking the inverse of 2 pi and 0 gave you the same thing.
Right.
Because it just mapped whatever point you had here to a point here and then took its inverse. Sorry, I said that way wrong.
Well,
If you were to take the inverse of 1, you would have gotten pi-halves. You wouldn't have gotten -3 pi-halves, even though that is also 1. When you did the inverse function, you only got 1. Because the inverse function is only defined on this restricted domain. So even though with the sine function, there's infinite places where you get 1, when you did f inverse of 1 on your calculator, you only got pi-halves.
right.
You didn't get these other points. Why didn't you get those other points? Because the inverse trig functions are defined on this restricted domain.
Well, I remember about the inverse function is like it didn't get above a certain number. It stayed within its stayed within pi halves.
The function, the value of the function stays between -1 and 1. The value of the inverse function stays between negative pi halves and pi halves. Okay, so by restricting its domain, we made a function that wasn't 1-to-1, 1-to-1, and then since it was a bijection now, it can have an inverse. Because remember, f inverse from y to x is only defined if f from x to y is a bijection. We only know how to talk about an inverse function if the original function was a bijection. Make sense? Okay. So that's it for restricting the domain of a function. Move on to the next scene. Probably one of the hardest things for students to grasp the first time they come across it with functions, and that is function composition. How many of you have come across function composition?
We already did it in our last class.
Oh, we did?
Function composition?
Oh.
Like in logic?
Oh, yeah, we did do it in logic, but he wasn't in logic.
I'm not saying our last class, like.
Yeah. Anyways, alright, let's just go over what it is. So function composition. So if we have f is a function from x to y, and g is a function from y to z, notice that what f maps to, g maps from. That's important.
Okay.
So f maps everything in x to something in y, and g maps everything in y to something in z. Then g composed with f, sometimes we read this g after f. G composed with f or g after f is a function from x to z. So it's combining these two functions together. F went from x to y, g went from y to z. When we do g composed with f, it feels backwards, but when we do g composed with f, we get a function that maps x to z.
Right.
And it cuts out the middleman of having to stop at y.
Right.
Okay.
So, then g after f, or g composed with f, is a function from x to z, and what does it do? By g composed with f of x is equal to g of f of x. So let's just see an example with what you would have seen in like a trig class, and then we'll do a more discrete example so that you can see it both ways. So let f be a function from the real numbers to the real numbers by f of x equals 3x squared. With me so far?
Okay.
And g is a function from the real numbers to the real numbers by g of x equals 5 minus 2x. Then, g composed with f of x, what is that? G composed with f of x, it's this. So g composed with f of x is g of f of x, right? But what is f of x? It's 3x squared. Right?
Okay.
And what do you get when you plug in 3x squared for g? What happens to g if I replace every x with 3x squared?
Yeah, 5 minutes.
I get 5 minus 2 times 3x squared, or 5 minus 6x squared.
Right.
Now let's look at f composed with g. F composed, notice I can do it either way on this one, because the output of this function is the same as the input of this function, so I can do g composed with f.
Yeah.
And the output of this function is the input of this function, so I can do f composed with g.
It's not necessarily on 2.
They don't have to be.
Well, I'm just saying, not every y is getting mapped to every x. Okay, maybe I'm thinking of it wrong, but not every y is being mapped in f of x. Yet you're using the y's as now your x in g.
Every x gets mapped to something.
True.
F takes x and maps it to something, and then
Right.
g takes that and maps it to something. Similarly down here, f after g of x is f of g of x, which is f of g of x. Now when you plug in g of x, or 5 minus 2x, into this function, you're going to get 3, 5 minus 2x squared. So we get 3, 5 minus 2x squared, right? And then just do the algebra here. When you square that, what do you get? You get 25 minus 20x plus 4x squared. That's just squaring this. I still left my...
Yeah, it should be a 3.
I don't know why I put a 5 there. Yeah, that should be a 3. So that's going to change these numbers. So that's going to be 75 minus 60x plus 12x squared. And notice that g composed with f of x is way different than f composed with g of x.
Yeah.
Order very much matters. It is not the same thing. Okay, now let's look at, well, are we good with this? Because I need to move the camera, so.
Yeah.
Okay, so let's move the camera and then we'll look at a discrete example. Don't want to go off. Someone look at it and tell me when I'm good.
You're good.
Okay,
No.
so a more discrete example. So we're going to make up 3 sets. We're going to say A is the numbers 1, 2, 3, 4. B is the numbers 1, 4, 9, 16. C is the number negative 3, 3, 13, 27. And F is going to be a function from A to B. And F is just going to square those numbers. And then G is going to be a function from B to C. And G is just going to double the number than minus 5. So F is going to be a map here. F is going to map A to B. What is F of 1? 1. What's F of 2? 4. What's F of 3? 9. What's F of 4? 16. So we mapped everything in A to something in B. That's what F did. It took all these values and mapped them to these values. G, what does G do?
That's B to C.
Yeah, G is a function from B to C, where it maps each number to 2 times that number minus 5. So 2 times 1 minus 5 is? Negative 3. I just drew these so they map nicely. Maybe we should change the order here so that you don't think that it has to be nice. So we got 27, negative 3, 13, and 3. Okay, so G maps 1 to negative 3. It maps 4 to 3. It maps 9 to 13. And it maps 16 to 27. So G maps everything in B to C. So now, notice, first off, I cannot do this. I can't do F composed with G. That doesn't make sense.
Yeah.
I can only do G composed with F. Right?
Mm-hmm.
Why?
Because I can't take, F cannot map things from C.
Oh, because it's reliant on F.
Yeah, I can only do F after G if F maps the outputs of G to something. Right? Because F of G of X is F of G of X. So F needs to take whatever G maps to and map that to something.
Right.
F doesn't know how to map things here.
Right.
It only knows how to map 1, 2, 3, and 4.
Right.
So over here, in this example, although we can't see it in the recording, since both the functions were from the real numbers and to the real numbers, you could compose in any order you wanted. Here, we can only do G composed with F. We cannot do F composed with G.
Because we don't have
It doesn't make sense. We'll do more with that in a second. Let's continue with this, and then we'll try and do the same thing with the other one, and you'll see where we get our problem. So, G composed with F of X then is going to be what? It's G of F of X, right? Which is equal to, what does G do? Or sorry, what's F of X? X squared. So it's G of X squared, which is equal to 2x squared minus 5, right? So now, let me write these down here further. Here's F, here's G. So now F composed with G maps from A. Maybe I'll just use a different color to try this. So now F composed with G we're going to do in blue, or G composed with F. G composed with F we'll do in blue. And what does it map 1 to? It maps 1 to
-3.
-3. So what maps 1 to -3? Notice that's the same thing as f of 1, or g of f of 1. This is the same thing as g of f of 1. What was f of 1? 1. What was g of 1? -3. So it does it all in one go. Instead of mapping all these values to these values and these values to these values, we cut out the middleman and we map it directly from this set to this set. That's intuitively what function composition does. So what is g composed with f of 2?
Now see where you guys can.
3.
Yeah, so you can plug it in here and you can think 2 squared is 4 times 2 is 8 minus 5 is 3.
Yeah, I thought.
Or you could think to yourself, what's f of 2? 4. What's g of 4? 3. And you can think about it either way you want.
I was getting stuck because that square.
But either way, 2
inclusive
goes
so I
to
thought it was
3.
making the 4. I thought it was making the 2 to 4. So like, no, let's say 1 negative 3.
And also notice that g composed with f, make sure you realize that this is a function from A to C. Right? That's what we're doing.
Yeah.
Okay. What does 3 map to? You can either plug it in here. 3 squared is 9 times 2 is 18 minus 5 is 13. Or you can think about it right here. F of 3 is 9, g of 9 is 13. Either way, you get 3 maps to 13. Finally, 4, think about however you want. 4 squared is 16 times 2 is 32 minus 5 is 27. So 4 goes to 27. Or think about it this way. F of 4 is 16, g of 16 is 27. Right?
Yep.
So that's what function composition does. Now let's see what problems we run into trying it the other way. Let's try doing f composed with g of x. Right? Now f composed with g is equal to f of g of x, which is equal to, well, we can write this first. F of 2x minus 5, which is equal to, what does x do? It just squares it. So that's going to be 4x squared minus 10x plus 25. Sorry. Should have written with more space. Anyways, so now, first off, what's the domain of this function? It needs to map whatever g maps, right? We need to plug something in that g can map and do that first. So pick something from g, or sorry, g can maps b, so we need to start in b. Right? I need to plug something into g, and then whatever g spits out, plug that into f, right?
Okay.
So what's something that g knows how to map?
1.
1. So start with g of 1, plug that in. What's g of 1?
4 minus 10 plus 45.
G of 1 is negative 3.
Yeah.
Now plug negative 3 in for f. You can't. F only knows how to map 1, 2, 3, and 4. This isn't defined on all real numbers. This is only defined from B to A. Or actually from B to B. is what that's trying to be. Which doesn't work. Maybe writing it out this way is confusing.
No, it actually.
No, it's.
But if we just keep it how we had it here, f of g of x. So first off, f composed with g has to be a function from the input of g to the output of f. So it has to be from b to b, so we have to be loopy on this. And then f of g of 1 is equal to f of -3 is equal to, that's not in there. -3 doesn't map to anything in f.
Right.
Make sense?
Mhm.
Okay. So there is function composition. Any questions there? Any more examples you want to see, or you think you're good? Good?
Mhm.
All right. Then let's move on to finite and infinite. So our next definition. We call a set X, or a set X is finite if either it's empty or if there exists a bijection from 1, 2, 3, 4 all the way up to n to x for some n in the positive integers. Now that seems like a lot, and that might seem confusing at first, but if you think about this, this is very intuitive. How do you know that this set, give me some objects, triangle, square, circle, is this set finite?
Yeah,
How do you know it's finite?
because there's only 3 objects.
Because there's only 3 objects in there. So you said there's 1, 2, 3 objects in there. So if I can make a mapping from the numbers 1, 2, 3 to this set, then this set is finite. If I can create a bijection from the set 1, 2, 3, 4, 5 all the way up to n for some positive number n to the set that we're talking about, then it's finite. And it's just doing that. You're assigning 1 to some object in there, you're assigning 2 to some object in there, you're assigning 3 to some object in there, and they each get assigned to one and only one object. So if I can make a bijection from the set 1, 2, 3, I cannot do 3 and end. If I can create a bijection from this set to this set, then I know that this set is finite, because this was all the positive numbers up to some positive number, n, in this case 3.
I don't understand why you say I can create a bijection. Because I thought bijection means you're on 2 and you're 1 to 1.
Right, I can create a function, a one-to-one function and an onto function from this set to this set. What is that function? That would be the function f is equal to, let's see, 1 goes to triangle, 2 goes to square, we could have also done 2 to circle, doesn't matter, and then 3 goes to square. There it is. A function that maps everything in here to one and only one object in here. If I can do that, then we say that the function is finite, and we could also define cardinality right now if we want, and we would also say that the cardinality, or the size of the set, is equal to whatever this n is.
There you go. No squash.
So I don't know if we make a note of that here. He should. May as well use it. But anyways. So a set x is finite if I can find a positive integer and a bijection from the set 1, 2, 3 all the way up to that positive integer to the set x. And furthermore, I can say then that the size of x is that n, that positive integer. Once again, one of those things that feels like dense a lot of notation for a concept that already feels pretty obvious to you. So we need to make sure that we have an understanding of what exactly it means for a set to be finite.
Mhm.
Feel like you're good with this definition? So if the set is empty, or if I can create a bijection from some set of the positive integers up to some was going to say finite set of positive integers, but I'm choosing the word to define it. If there exists a positive integer such that 1, 2, 3 up to that positive integer, I can create a bijection from that set to the set we're talking about, x. And then, this is the hardest part of the definition, if a set is not finite, then we call it infinite. Infinite. That's what it means to be infinite. No bijection exists.
Okay.
So if the bijection exists, it's finite. If the bijection doesn't exist, it's infinite. Good? Okay. Now we have another notion called countable. A set X is countable if it's finite, or if I can create a bijection from all the positive integers to the set. In other words, if I can create a bijection from the counting numbers to the set, then it's countable. In other words, I can count everything in it. I can assign everything a counting number.
Isn't that the definition of finite?
No, that's countable. So for example, the integers are countable. How can I count the integers? I need to map every single positive integer to an integer to show that the integers are countable. How would I do it? I could map. So here's my input, here's the output I'm going to map it to. I can map 1 to 0, 2 to 1, 3 to -1, 4 to 2, 5 to -2, 6 to 3, 7 to -3, etc. And I can keep mapping like that. And I will map every positive integer to every integer.
Okay.
Right? Another way that we could write this function, what does this function do? F of n is equal to, let's see, it's going to be equal to n divided by 2 if n is even, and let's see, negative n minus 1 divided by 2 negative if n is odd. Right? Did I do that right? So f now is a function from only the positive integers to every integer.
Okay.
X does not have to be every integer.
No, this is just one example.
I see.
All that we require is that we map every positive integer to something. In this case, I'm mapping every positive integer to an integer. So, the integers, this set over here, is countable. Is it finite?
No.
No! There's an infinite number of integers.
Mm-hmm.
So, countable and finite are not the same thing. All finite sets are countable. Some infinite sets are countable. You with me?
Mm-hmm.
So, here's an example. What's an example of a set that isn't countable? An example would be the real numbers. There is no mapping you could make from the positive integers to the real numbers. And we won't bother proving that unless you guys are really interested in it, then maybe I can set that proof up next time. But anyways, so that's what we mean by countable. Good? Any questions on countable or finite or infinite? Okay. Oh, hold on. Is this function a bijection?
Yes. No, it's not. It's not 1-to-1.
if this function isn't a bijection, then I did not show that z is countable. The only way I can prove that z is countable is if I can find a bijection f that maps every positive integer to z. So this has to be a bijection. So let's make sure we understand that this function is a bijection. Now you said it wasn't which one?
1, 1.
It's not 1 to 1?
Oh yeah, it is actually. Because 1 is not the same as -1.
So, is there a property here that's not obvious to you guys that it has?
No.
Can you see it's 1 to 1?
Yeah.
Yeah,
Can you see that's on 2?
Yeah.
yeah.
Okay, then we won't bother with it. So yeah, we had to find a bijection from this set to this set to show that this set was countable. This was a bijection proving that the integers are countable. Okay. Let's try and finish up here. So the author has a bunch of theorems that he listed but didn't prove. Let's make sure that they at least appeal to your intuition. So a subset of a finite set is finite.
Yes.
That appeals to your intuition? Okay. A finite union of finite sets is finite.
Yes.
That appeals to your intuition? A finite product of finite sets is finite. Good? A subset of a countable set is countable. Take a subset, you couldn't have made it bigger.
Okay.
Right? A countable union of countable sets is countable.
Mm-hmm.
That one might not be as obvious to your intuition. How would we count those? So let's say we have a countable number of countable sets. How would we count those? So let's say, maybe I'm overthinking it because you guys aren't used to proofs like that. Never mind. We'll just stick with the going to your intuition for now. A countable union of countable sets is countable, and then a countable product of countable sets is countable.
Okay.
What would be a countable product of countable sets? That would be something like z cross z cross z. There's a countable product of countable sets.
Okay.
Oh, because there's literally. Okay, yeah.
That's what they mean by that. Okay. Moving on, next definition, sequence. Those of you who have done calculus better understand what a sequence is, but let's go over it. Given a set X, a sequence in X is a function whose domain is all the positive integers. So I take X and I map every positive integer to something in X. That's how I create a sequence in X. The range of F, our function, our sequence, is just called the range of the sequence. Sounds very complex, but when you see a few examples, it's going to click just fine. So, before we do that, let's just think of a sequence. Here is a sequence. Remember, it needs to be a function that maps all the positive integers to any set we want to create a sequence in it. What should we map to? Let's keep it simple, just say the real numbers. Good so far?
Okay.
So I'm going to create a sequence in the real numbers, so this is called a real valued sequence. By what sequence should I choose? F of n is going to equal just 1 over n. So I need to map every positive integer to some real number. So what do I map 1 to?
1.
Yeah, so I mapped 1 to 1. What did I map 2 to?
1/2.
1/2. What did I map 3 to?
1/3.
1/3. What did I map 4 to?
1/4.
1/4. And etc. I can keep writing out what this function is, right?
Mm-hmm.
So functions like this, functions that map every real or every positive integer to something, are a sequence, and they're a sequence in whatever the set is that you're mapping to. So this is a sequence in R. Notice we didn't use all the real numbers, we only used some of them. So you don't have to use all of R. This isn't a bijection. It's just a function whose domain is all the positive integers.
Okay.
You with me? So this is a sequence. I could have also changed this to just rationals, right? And called this a rational valued sequence. In calculus, we only dealt with real valued sequences. So it was always f from the positive integers to R. They were always real valued sequences. But you could have rational valued sequences. You remember what rationals are? All the possible fractions you can make. If I can, with integers. If I can express it as an integer over an integer, it's a rational. So that's still rational, that's still rational, that's still rational, etc.
Okay.
Okay. So let's go back and say what this is again. Given a set X, in our case we're using all the rationals. A sequence in X is a function from the positive integers to X. That's what it is. A sequence in Q is a function from the positive integers to Q. Here's one. We could have made infinitely many of them. The range of f is called the range of the sequence. So the range of this sequence is what?
1, 1/2, 1/3, 1/4.
The range of the sequence is all the right-hand values. So we got 1, we got 1/2, we got 1/3, we got 1/4, etc. Right?
Mm-hmm.
Now notice, when we're creating a sequence, we already know what all the left-hand values are going to be. It's just going to be 1, 2, 3, 4, 5, 6, etc. All we really care about are the right-hand values. What do the right-hand values of the scene look like, right? 1, 1/2, 1/3, 1/4. So sometimes when we write a sequence, instead of writing it like this, we like to write it like this, where the first number is just whatever 1 maps to. The second number is just whatever 2 maps to. The third number is just whatever 3 maps to. So this is shorthand for writing this.
Okay.
Make sense? In calculus, we use curly braces instead of parentheses. In this class, we use parentheses. So don't get confused by that. So let's go back to this. The range of f is called the range of the sequence. So this is the range of the sequence that we're listing out here. Notation is just exactly what I started doing over here. If we have some sequence, we denote f of n by xn and express the sequence as x1, x2, x3, or just xn. So in our case, xn was 1 over n, and we can express the sequence as x of 1, x of 2, x of 3, x of 4, or we could have just expressed it as a sequence 1 over n. So if you see 1 over n in parentheses like that, this is shorthand for this sequence, because obviously we can't write out all these numbers. The same way that f of x equals x squared was a shorthand for a function, this is shorthand for a sequence.
Okay.
This was a particular function, this is a particular sequence, right? Shorthand for the sequence 1 over n, shorthand for the function x squared. Because what is f of x equals x squared really? It's all the set of ordered pairs where we map a number to its number squared. So we would map 2 to 4 would be in here. We would map 0 to 0. We would map square root of pi to pi, etc. There's infinite things in there. We can't list everything in there, so we have this nice shorthand for talking about this whole set. Well, when we know our set has a special property where its domain is just positive integers, then we have an even smaller shorthand for expressing that function. Because it's a special type of function, it's a sequence. And so here's how we like to express a sequence. And just like I use f of x as a generic function, right? If I was doing some proof about a function and I didn't know anything about the function, I'd just say f of x, right? Let f of x be a function such that blah, 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 blah. Similarly, we use let x sub n be a sequence such that blah, 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 blah. And what is f of 1? It's whatever f maps 1 to. What is x sub 1? It's whatever this sequence maps 1 to, or the first term in the sequence.
Okay.
Make sense? Okay. So that's exactly what I wrote right here. We have some function that maps n to just 1 over n. What does that sequence look like? 1, 1, 1, 2, 1, 3, 1 over 4, or just 1 over n? So now tell me the first term in this sequence. So here's another sequence. Sequence 2n over n plus 1.
1.
The first thing in there is 1. What's the next thing in there?
4 thirds.
4 thirds. What's the next thing in there?
2 thirds. 6 or 4 6.
6 over 4
6.
or 3 over 2.
Yeah.
Right?
Yeah.
What's the next thing in there?
2 over
8 fifths. I don't know what you were thinking. What's the next thing in there?
10 over 6.
Or
5 over
5 thirds. Okay, etc. So if I gave you this sequence and said, write the first 10 terms in the sequence, you know how to do that, right?
Yeah.
And if I said, what's the 27th term in this sequence?
54 over.
Then it's just 54 over 28, right?
Yeah.
Right. So you can find whatever term in the sequence I told you to find. So that's what a sequence is. It's just a function whose domain is the positive integers. And we typically express them somehow like this. Unless we're talking about a generic one, then we just use x sub n. Okay. Last thing, subsequences. Subsequences have an atrocious definition when you first read it. It's very confusing. So first we're going to just create a subsequence, then we're going to go read the definition. Alright, so give me a sequence we want to start with.
What do you mean?
Give me any sequence.
1 over n.
Okay, we'll use 1 over n. So what's the first term in the sequence? 1 over 1, then we have 1 over 2, then we have 1 over 3, then we have 1 over 4, then we have 1 over 5, then we have 1 over 6, 1 over 7, I don't know how many I'll need to get the point across. We'll go to 10. Here's the first 10 terms in the sequence, obviously it goes on forever. Now, I am going to create a subsequence from this sequence by choosing terms in the sequence that I want. Only rule is, I have to pick infinitely many, I can't ever stop, and I can't go backwards. I can't pick this one and then pick this one.
Okay.
I have to go through every term of the sequence and decide, do I want to keep it or not? Do I want to keep it or not? Do I want to keep it or not?
Didn't we decide the limit of a sequence is of the subsequence?
If a sequence converges, then a subsequence converges to the same thing as a sequence.
Yeah.
Anyways, so here's our sequence, so let's create a subsequence. What should we do? Should we pick,
1.
should we take 1 over 1?
Yes.
Yeah, okay, we'll use 1 over 1. What about 1 over 2?
No.
No.
No. What about 1 over 3?
Yes.
What about 1 over 4?
No.
What about 1 over 5?
Yes.
What about 1 over 6?
No.
What about 1 over 7?
Yes.
So he wants every other one, it looks like.
Yeah, but.
Okay, so we can continue the sequence using every other one. That's a valid subsequence. Right?
Yes.
So we're going to construct a third sequence now, keeping track of all the indices I chose. I chose the first one, so that's 1. I didn't choose the second one. I chose the third one. I didn't choose the fourth one. I chose the fifth one. I didn't choose the sixth one. I chose the seventh one. Didn't choose the 8th, chose the 9th, etc. Right? Okay, so for our definition when we come up here, this is going to be x sub n is equal to this thing. This is going to be n sub k equal to this thing. And this is going to be y sub n or x sub n sub k.
Y sub
And we have 3 different sequences that we're talking about here.
Y sub k, not n.
Y sub k. Thank you. Okay. So, let's read the definition now and wrap our head around all these. Let xn be a sequence, and let n sub k be a sequence of increasing positive integers. These are increasing positive integers. That is, the first one has to be less than or equal to the second one has to be, or sorry, the first one has to be less than the second one has to be less than the third has to be less than the fourth has to be less than the fifth, etc. In other words, just choose a bunch of indices, but make sure that they're increasing order. You can't pick indice 5 and then indice 2. If you pick indice 5, your next one has to be bigger than 5. So, restart. Let xn be a sequence and let nk be a sequence of increasing positive integers. Then the sequence y sub k by y sub k is equal to x sub n sub k is a subsequence. What is y sub 1? It is equal to, using our definition up there, what should y sub 1 equal?
1. 1 over 1.
Well,
It should equal
Yeah.
x sub n sub 1. So it should equal x sub n sub 1. But what is n sub 1 equal to?
1.
What's the first term in our n sub k sequence? 1. So it should be equal to x sub 1 sub 1.
okay,
What is the first term?
go up.
It's just 1. 1 sub 1. Sorry,
You want x.
I mixed up.
Yeah.
N sub 1 is just 1. So it's equal to x sub 1.
Yeah.
Y sub 1 is equal to x sub 1. The first term of this sequence is equal to the first term of this sequence. Let's find y sub 2. Y sub 2. Y sub 2 is equal to x sub n sub 2. What is n sub 2?
3.
3. So it's equal to x sub 3.
Interesting.
You see what we're doing?
Yeah,
Let's do the one more. Make sure we got it. What's y sub 3 equal to? X sub n sub 3, which is equal to
5.
X.
x sub 5. And probably should have written is equal to 1 over 1, is equal to 1 over 3, is equal to 1 over 5. So that's all that's happening here, and that's why we just use x sub n sub k to represent the subsequence typically instead of some other letter y. The author just didn't want to confuse you when giving you the definition. So we created a subsequence x sub n sub k from x sub n, where n sub k is a sequence of indices. Simple idea, but a ton of notation behind it. When you want to create a subsequence of a sequence, you need to create a sequence of indices first in increasing order. Think you got it?
I have calculus.
Let's try this a different way. Make you reverse this. See if that helps. So just try and use the definition. Don't try and use what's obvious just because we're writing out simple sequences. So let's say that I tell you x sub n is equal to the sequence n over n plus 1.
Okay.
Okay, there's my sequence. Sorry, we don't need that there if I tell you. So x sub n is just a sequence where the nth term is given by this, right?
Mhm.
So, and then I also tell you that n sub k is a sequence equal to 2n plus 1. Those are increasing positive numbers, right? So this is valid, this is valid.
That's a sum.
So now my question is, x sub n sub k, my subsequence, is equal to, what's the first thing in here?
1/2 1. 2. It's gonna be 2.
It's not 2, so.
Yeah.
What's the first thing in here? So we know that x sub n sub k is equal to x sub n at 1. What is n at 1?
3.
3, right?
Yeah.
So this is equal to x sub 3, which is equal to,
3/4.
where's that? We're just doing x sub n at 1 is equal to, x sub 3 is equal to what?
3/4.
3/4. So the first term in here is 3/4. Let's find the next term. What is x sub n sub 2 equal to?
5/6.
x of 5, which is equal to 5, 6. So it's 5, 6. And then what's the next thing in there?
6, 7.
7 eighths.
Try me again.
Think you got it?
Yeah.
Okay, so that's what subsequence is. And then that ends our preliminary stuff.
That's the end of chapter 0.
That's the end of chapter 0, I think. Yeah, then he just has examples, but we've done better ones than what I have here. So yeah, next time we'll actually be able to start topology. You're going to learn what topology is next week.
This is pretty cool.
And we're only on like lecture 10, so fast-paced class.
Yeah.
Is it for real lecture